in behalf of Qatif Astronomy Society, CAS, today I would like to interview with a physicist who has been working in the field of foundation of physics and cosmology since 1990s. Dr. Rafael Lopez-Mobilia is working now as a faculty member at the at the Physics Department, Physics and Astronomy Department at the University of Texas at San Antonio, UTSA. Dr. Lopez-Mobilia got his bachelor in physics from Catholic University in Lima, Peru. His master degree from the University of Notre Dame, Indiana, and his PhD from the University of Texas at Austin. In 1995, his doctoral research was done under the membership of Professor Steven Weinberg, who received the Nobel Prize in Physics in 1979. Dr. Lopez-Mobilia is experts in the theoretical physics. He has published paper in particle physics, cosmology, and mathematical physics. His main interest at the present on foundation of quantum mechanics. I was lucky to have him as the supervisor of my PhD dissertation. Welcome, Rafael.
Thank you. My pleasure. It's my honor, actually, to have this interview with you, Anwar.
Well, today we have some question to be discussed with you about the open questions in physics and cosmology. Well, let us start with the recent achievement. Last month, on April 10th, the first image of black hole was made public. How do you see the impact of this scientific achievement? And do you think it is a breakthrough? Let me just recall the statement of Michael Kramer, a director at Max Planck Institute for Radio Astronomy. He said, the history of science will be divided into the time before the image and the time after image. How do you think that?
Well, it was certainly a breakthrough, a really important one. I don't think I agree with that statement. It's a little too much, like before and after. It's certainly a very important development, absolutely. And I was actually waiting for the time that I've been waiting since last year to see that image, and it was really impressive. So it's certainly a breakthrough. It's very important, and it's just the beginning. I'm sure that they will soon start refining this and using more radio telescopes to get even better image, more resolution. They will probably image the black hole at the core of our galaxy, which they were also trying to do, but they decided first to publish these results. So it's really important and very impressive, and certainly the beginning of a new kind of astronomy. So now dividing science before and after, it's probably a little exaggerated. At least in my opinion, I don't know.
Right. Yeah, you're right. I mean, I think that instant or that achievement, at least show how is the powerful of science. They can at least image that small, tiny part, from that long distance. Something like about 65 55 million light year, yeah. And with a small area which is like the size of solar system. Right. So that's really something.
It's amazing.
It's amazing and impressive. Yes. So let us now talk about the Open's question. As you know, dozens of fundamental questions in physics still do not have an answer. For example, Wikipedia lists over 100 of main and secondary open questions. Well, what do you think? That those questions really they start all the way from quantum to plasma physics, and it seems they are growing. They are still the list is get large, so get higher. So my question is that what do you think are the main reasons behind this number of unsolved questions?
Well, there have always been lots of unsolved questions. Maybe the number is growing because we keep learning more and more. I mean, the more we learn, the more new questions that appear naturally. So usually those who don't know anything don't have many questions, actually.
Right.
Just a few. The more we know about cosmology, the origin of the universe, the size, the shape of the universe, the fundamental laws of physics, applications of those fundamental laws to other disciplines, the more questions, of course. So we will keep learning more, understanding more, but at the same time, I suspect that the number of questions will keep increasing.
Right, right. Actually, I think that reminds me of the statement of Isaac Newton. He said, the much I know, how much I ignore.
Exactly.
So it's something like that. Yeah,
Mm-hmm.
right. Well, let us, talk about some of the main unsolved problems. Which question do you think, if we want, to list some of these, unsolved question or unsolved problem, what do you think is, the main or comes in the top of these questions?
That's a difficult question itself, and it depends a lot on your own prejudices.
Mm-hmm.
It depends on who you ask. I mean, in my case, because the area I know the best is theoretical physics, specifically particle physics, quantum field theory, cosmology, maybe I should restrict myself to that area. And because there are lots of very important questions in other areas like in biophysics, atomic, etc. So
but what is the most impact,
to me, a crucial one that is central is the quantization of gravity. That's one. Another one that's really important to me is understanding quantum mechanics. Understanding what quantum mechanics is telling us about the nature of reality. That's one thing that still hasn't been clarified completely. We know how to use quantum mechanics. We don't know exactly what it means deeply. The nature of time is another important one, which is connected with fundamental physics, quantum mechanics in particular, quantum gravity. There are lots of other questions like in cosmology, what is dark matter, what is dark energy, whether inflation actually happened, and what model of inflation is the right one, assuming that inflation actually occurred. In particle physics and quantum field theory, supersymmetry, which is an idea that's been around for decades, a very important, deep idea. We don't know yet if supersymmetry actually is true. In nature, there were big hopes that at the Large Hadron Collider they would discover evidence for supersymmetry. So far, nothing. So there has been no indication that supersymmetry is there. So those were with some of the deep questions I think that right now are in the minds of most theoretical physicists.
Right. So before getting into this unsolved problem, can we say that we are now almost in an era of a new physics? Are we now in a transition era where we expect to have some new physics?
I think so.
Yeah. Good.
First of all, I think that we should be able to find out what is dark matter relatively soon. In the next few years, we should be able to know. Supersymmetry, for example, could be an answer to dark matter. We should be able to either find that supersymmetry is a feature of fundamental physics or not also in the next few years. We may be able to find evidence for the so-called B-mode polarization in the cosmic microwave background radiation, which would indicate that inflation actually occurred. It would be very strong evidence for inflation and for other fundamental physics stuff. So all of that should happen within maybe the next 10 years, I suspect. And any of those would be really important advances in physics, in fundamental physics.
Right. So again, which of them you think comes in the top, or comes first?
Maybe quantum gravity would be the top one.
Why?
Because we have been actually trying to find out whether space-time itself is subject to the laws of quantum mechanics or not. A quantum theory of gravity would be the answer to that. And maybe, most likely actually, it would change the way we understand the physics of space and time. It would answer questions perhaps about the origin of the universe, whether everything started in a singularity or not, the nature of black holes, whether or not Hawking radiation actually is a true feature of black holes, whether there is a singularity inside black holes, and the nature of those singularities, or whether maybe they don't exist. It should answer many, many fundamental questions. It's I would say, one of the holy grails of fundamental physics nowadays. String theory is one possible answer to it. Loop quantum gravity is another one, but nobody knows whether they are actually true. So they're still speculative. So that's a really important one. That would be probably the number one, I guess.
So do you think that will prove, the space-time itself, or?
Nobody knows. I mean, maybe a quantum theory will actually be an entirely new way of looking at physics. Maybe even at quantum mechanics. Maybe space-time at the quantum level is not space-time. It's something entirely different. And perhaps space-time emerges at the microscopic level, like a limiting case of that something else which is not space and is not time. So maybe with a quantum theory we'll be able to understand also the deep nature of time, how time emerges from that more fundamental physics. Maybe we will have a new way of looking at quantum mechanics, because so far, even in attempts like string theory or loop quantum gravity, quantum mechanics is taken at face value. So you don't modify quantum mechanics, you don't explain quantum mechanics. Quantum mechanics is assumed to be true, valid, and you use it in developing these other theories. Maybe if we finally develop a fundamental quantum theory of gravity, maybe it will require a modification of quantum mechanics, not only of general relativity, but maybe quantum mechanics itself. Who knows?
Yeah.
And all of that would be really, really deep. It would be a fundamental step forward in our understanding of basic physics.
Well, now, don't you think that the evidence of that image, the image of black hole, which shows the space-time, and specifically the Kerr space-time, because you can see from the image, the brightness of that image was in one side, and the other side is almost we have weak brightness. That really shows that evidently shows there is what is called Kerr space-time. So the image or the evidence from that image, it shows the space-time itself. So you mean that in some level, or in the micro level of space-time, you are talking about?
Right. I mean at the microscopic level, probably space-time doesn't look like space-time. And at microscopic, I mean at the so-called Planck scale, which is much, much smaller than even an atomic nucleus or a proton, or so a scale that's much, much smaller than that. Yeah, at the microscopic level, like black holes, etc., our description of gravity seems to be perfectly adequate, like general relativity. And so far, all the predictions have been confirmed pretty well. So there would be no major changes at that scale.
Yeah. Well, how do you think, how do you think, or how to solve this problem? What do you think, the avenues to overcome the problem, or to solve this problem?
But if you mean quantum gravity.
Quantum gravity, yes.
Right. Well, that's a very difficult answer to give, because really nobody knows. Again, the main approaches right now are string theory and loop quantum gravity, and many more physicists are working on string theory than in loop quantum gravity. They're very different approaches. They have had some successes at the theoretical level. The problem is there have been no predictions that you can go and test in the lab, experimental predictions, and probably it will take still a long time before any of those predictions can be confirmed or disconfirmed experimentally. That's the problem. So that's why we don't know whether either approach is the right one to quantum theory of gravity. Now, both are quantum theory of gravities. I mean, of gravity. The thing is whether they are right or not. So that's the main question. Whether, for example, if string theory is the correct way of doing quantum gravity. Nobody knows. Okay? People working in string theory, many of them are convinced this is the right approach, but they have not been that successful in convincing others outside the community of string theorists that this is the right approach. And part of the reason, again, is there are no experimental predictions that you can verify or refute. And so far it's mostly speculative. It's very difficult. I mean, the mathematics are very advanced, and so the theory is still not well understood, not even by the experts. They have not been able to derive the theory in a simple manner from some basic simple principles, like, for example, in general relativity, the principle of equivalence. Say, there's nothing like that in string theory from which you can say, okay, this is the way, and this is a unique theory. In fact, there are many different ones. It's difficult to say this is a unique theory that explains our universe. They haven't been able to do that. In fact, it may be impossible, actually. String theory seems to imply maybe even a multiplicity of possible different universes, some sort of multiverse, kind of like what happens in other areas of physics, like in inflationary cosmology, or in the many worlds interpretation of quantum mechanics. It's difficult from the theory to say this is the unique prediction and this happens to agree with the universe that we observe. So now other approaches, I don't know. People tried in the past to quantize general relativity, the so-called canonical way, more or less the way you do it with other quantum field theories. It didn't quite work. You get infinities in the calculations all over the place, which are uncontrollable, so the theory is fundamentally non-renormalizable, so they had to start from a completely different approach. In the case of string theory, it was kind of accidental. They were not looking for a quantum theory of gravity. They found accidentally in the 1970s that gravity seemed to be contained in the theory, even though they were not looking for that. They were trying to do something, they were trying to explain the strong interactions in particle physics. They were not trying to explain gravity. But it was kind of like a bonus. And in a way, that was what excited many physicists the most, when they realized that, oh, maybe this is actually a quantum theory of gravity.
Yeah. Well, I think some results of that string theory is like the multi-dimension or higher dimension. Would you elaborate more on that?
Yeah, that's actually something that is required by the theory for its own self-consistency. So, unlike in other theories in physics, like in quantum field theory and particle physics, in principle you could work in any number of dimensions for space-time. I mean, space-time seems to have 4 dimensions, 3 of space, 1 of time. String theory requires 10 dimensions, 9 of space, 1 time. Or else the theory itself doesn't work. Doesn't make sense. So, excuse me, the mathematics itself, in order for self-consistency of the theory, required 10 dimensions of space, and which is it was kind of, I suppose, very surprising, very unexpected to the physicists who initially were working on string theory, because it hadn't happened before in physics, as far as I know, that a theory had had to be developed in a specific number of dimensions, or otherwise it wouldn't make sense. Actually, initially the theory predicted 26 dimensions, but then they incorporated fermions, particles with half-integer spin in the theory, and in that version it requires 10 dimensions. They didn't quite know at the beginning, but that automatically meant that the theory contained supersymmetry. And so when they found out about it, the theory came to be known as superstring theory. And for many years it was called superstring theory. Then physicists went back to calling it just string theory. I guess it's easier, simpler to call it string theory. But it requires supersymmetry. It's a key ingredient, which again makes it concerning, the fact that there has been no indications of supersymmetry at the Large Hadron Collider. Most theoretical physicists were convinced that we were going to find evidence for supersymmetry at the Large Hadron Collider. It hasn't happened, which is very, very strange, very puzzling. So,
well, I mean, if we incorporate, more particles, you say when they incorporate fermion, they reduce it from 26 to 10.
Yeah.
Now, if we incorporate like more particles, let us assume that they discovered a new particle, and they incorporate it. In that case, are they going to like reduce the number of dimensions?
I don't think so. No, what they did was not really incorporate new particles. They incorporated spin 1/2, spin 3/2, so half-integer spin states instead of only just integer spin states. So because we know that there are both in nature, so the number of particles is actually, and the different types of particles, species of particles, is predicted by a theory. So different vibrational modes of the string correspond to different types of particles. So you can have open strings, and you can have also closed strings. Gravitons, that would be the carriers of the gravitational force, they would be closed strings. And so with a spin equal to 2. So that's integer spin. So you don't add particles to the theory, different types of particles. The theory itself predicts a virtual infinity number of different particles, essentially.
So this is the minimum number of.
I suppose so. Yeah, that's essentially. But of course, that doesn't mean that the theory is wrong because it predicts 10 dimensions. Because it was already discovered in the mid 1980s that there is a way to make sense of these extra 6 dimensions. There's a way to compactify those dimensions, close them on themselves, make them very small so that we don't effectively see them. What we see is essentially just 4 space-time dimensions, and the other 6 could be microscopic and finite, closed, like little loops. And so, and in fact, actually, that process of compactifying those extra dimensions would allow us to explain the other forces of nature, like electroweak and strong forces. So it's not really a problem with theory. In fact, it may be actually an advantage to the theory, the fact that it has extra dimensions, because it could explain not only gravity at the quantum level, it could also explain the other forces. That's why they call it a theory of everything, because it would be able to explain all the fundamental forces in a single framework.
So sometimes they use like the higher dimension to explain some phenomena.
Right.
Yeah.
Those extra dimensions could provide part of the answer to why the other fundamental forces of nature.
Oh yeah. And how to visualize, this higher dimension?
Well, again, visualizing it's very difficult. I don't think that. We're limited beings, and so it's the same way that we cannot visualize a black hole like the one that just imaged. It's so massive, so big, so that we can see this tiny image from a distance, but trying to develop an intuition of how incredibly big that thing is beyond our ability to visualize things. And so visualizing more than 4 space-time dimensions is virtually impossible for us. maybe computer programs, etc., could help you with maybe one extra dimension, trying to develop some visualization of an extra dimension of space, but not much more than that. It's really it's not easy.
Yeah. Well, let us assume that they solved the problem of quantum gravity. Will that be the end of the game, the end of science, or what is the consequence? Let us assume they solve it. What is the main consequence?
I doubt it, because like we were talking about before, every time you take a step forward, new questions, questions that we were unable to even ask before. We couldn't imagine those questions before. New developments, new understanding allow us to think of new questions. And so at the moment, we may think that if we go that far and we explain things at such a fundamental level, that would be it. Most likely when we get there, we'll have lots of new questions that we couldn't even imagine before. I mean, the ancients, they could imagine stuff like quantum mechanics.
Right.
They could imagine half-integer spin particles, bosons and fermions, or quarks inside protons. They could not ask any of those questions. It was when we started developing better understanding of fundamental physics, and we did experiments, and we discovered the atomic nucleus, and then protons and neutrons, etc., then we could ask more questions. So at the moment, the number of questions about that fundamental physics are limited. If we get there and we develop, say, a quantum theory of gravity, I'm pretty sure new questions will arise. And so this is probably an unending adventure. I don't think that we will get to the point that we say, okay, this is it, now we understand everything.
So you don't believe of that,
I don't think so.
Theory of everything that, it's like the ultimate theory of everything.
I personally don't think we will get there. We have felt in the past, already at the end of the 19th century and early 20th century, that we were getting really close to a theory of everything. Early in the 20th century, there was this generalized belief among physicists and chemists and other scientists that we're really, really close to a theory of everything. And in fact, probably that was going to be Maxwell's theory of electromagnetism. Many of them thought that with Maxwell's electromagnetic theory, they were able to, most likely they were going to be able to explain everything, like even gravity and classical mechanics. Everything was going to be derivable from electromagnetic phenomena. They were completely wrong, of course. They were completely wrong. I mean, they didn't expect the quantum to happen. Nobody was expecting quantum mechanics to be discovered. I mean, to become a fundamental part of physics. It was totally unexpected. Relativity, to some extent, was also unexpected, but probably quantum mechanics more so.
Right.
And some of the consequences, we still don't fully understand quantum mechanics.
I think quantum it's like a new idea. However, theory of relativity, it comes like as a consequence of some postulates like Poincare, like Lorentz transformation. So there was like what's called an introduction to that theory. However, the idea of quantum is really like a brilliant idea. It comes from Planck. He postulated that this way, the universe work in that way. Right. So that's good. Well, let us now move forward. What do you think it comes next? After the gravitational theory.
Well, again, my own inclination, my own taste. It doesn't mean that quantum gravity is actually the number one, because some other physicists would tell you something else. And in my particular case, in my particular case, I am especially interested. I'm especially fascinated by quantum mechanics itself. Understand quantum mechanics. I think that's a fundamental problem, a fundamental question that we're still struggling to resolve, to answer. Like I said before, we know how to use quantum mechanics. Every physicist knows how to use quantum mechanics. But at the same time, like Feynman famously said, he said that probably nobody understands quantum mechanics. So, meaning that we don't know exactly what it means at a deep level. For example, the measurement problem. Whether collapse is a real feature of quantum mechanics or not. Whether there's a fundamental chance, fundamental randomness in nature. Some physicists insist, absolutely, there is a fundamental randomness. It's there in quantum mechanics, it's clear. Others say, no, that's not the case. There's no consensus about it. My own take on that is, I do believe that there is a fundamental randomness, a fundamental chance in some processes at the quantum level. And I think that actually magnifies all the way to the macroscopic level, which would mean that even at the macroscopic level, physics is not entirely classical. So I think those are fundamental problems that need to be resolved. Some physicists believe that because they haven't been resolved, like Weinberg himself actually, some of them, like Weinberg, think that probably means that we should try developing some other theory, some more general or deeper theory from which quantum mechanics is found as a limiting case. So maybe quantum mechanics is not quite right. We need something better that we'll be able to understand deeply, and then quantum mechanics will be derived from it. I personally don't think that is the right way to approach it, because there has been no indication so far, no experiments ever, that quantum mechanics is wrong. So, which by itself is an interesting question, an interesting problem. Why is it that after 100 years of doing quantum physics, we haven't found any violation in any experiment, in any situations, no violation of quantum mechanics whatsoever? And every time physicists try to develop an alternative to quantum mechanics, some generalization, they end up with theories that don't quite make sense. They make predictions that are obviously wrong or inconsistent with relativity or things like that. So, by all indications, it looks like quantum mechanics is probably here to stay. It's probably maybe a fundamental part of some really basic theory of nature. We don't know, and the fact that we don't understand it well, to me, is an important problem that still needs to be resolved. I mean, so others probably would tell you, well, maybe not. Quantum gravity is certainly more important, and problems in cosmology, but I have the suspicion that a better understanding of quantum mechanics probably will help us developing a quantum theory of gravity, will help us understanding the early universe, a lot of stuff, because it should help us understand the nature of time better. So I think it's connected with many other fundamental problems. That's why I find it especially important and fascinating.
I mean, if we went past, before the science developed by generalization. For example, Newton has a good theory, but later on when they discover the theory of relativity, quantum or Newton law become special case of that, that theory. So in the same sense, do you think that quantum mechanics may be a special case with more a special case for more general theory?
It could be.
Yeah.
It could be. We have no idea how to do that, how to generalize it, but it could be. Now, it may be that there is some deeper, more general theory that's completely different from quantum mechanics. Instead of just a generalization, it's something entirely different. Maybe. That's what happened actually with gravitation. It's not that the Newtonian theory was generalized into a different theory that kind of looks like it, but it's more general. General relativity, which is that generalization, is completely different, entirely different. At the core, at the fundamental level, is completely different from Newtonian gravity. It doesn't even explain gravity as a force. It's just a consequence of curvature of space-time. So it's not even a force. So it's very different from Newtonian gravity. Maybe it will be something like that with quantum mechanics. Maybe there is some other theory that explains the fundamental physics at the microscopic level, etc., in an entirely different way, with entirely different concepts. And then somehow quantum mechanics can be derived from it, maybe.
So as for the randomness problem, you say that the randomness problem is still there. Do you believe there is like
Yes.
An actual, real randomness?
Mhm.
But in macroscopic manifestation, how to say, we have like what's called like the projection of randomness from microscopic level
mhm.
to macroscopic level.
Right.
How can we like explain it for public?
Well,
what is the manifestation, but macroscopic manifestation?
Every time that we perform a measurement of a quantum system, in principle, that's what's happening. Because, let me give you an example. Hopefully it's a simple example. An elementary particle has spin, which is, in everyday terms, is almost as if the particle is rotating. Elementary particles are not rotating, but that's one of those strange things about quantum mechanics. So it is as if they're rotating. And so if it's rotating like this, we say that it has a spin up. If it's rotating like that, we say it has spin down. For microscopic objects, things can be rotating always in one direction, and that's it, and a specific direction. Elementary particles could be, at the quantum level, doing these rotations in both directions at the same time. They are said to be in a superposition, in a quantum superposition of these two different rotational states at the same time. Now, does it mean that the particle is actually doing this and that at the same time? No, that would be a classical way of visualizing it. It's more subtle, and it's much, in fact, it's impossible to visualize at the macroscopic level. So for us, it's beyond our intuition. We can mathematically discuss it. I mean, we understand the mathematics that perfectly consistent and right, but trying to visualize what's going on is beyond our puny brains. So anyway, so if you have a particle in that quantum superposition of being in the spin up state and also spin down state at the same time, and if you measure the spin, quantum mechanics tell you that there is a probability of getting a spin up and a probability of getting a spin down. Suppose that we set up things so that it's a 50% probability you will get spin up, 50% probability you get spin down. According to quantum mechanics, that's a fundamental probability. It's not that before you measure it, it's actually spin up, rotating like this, or actually spin down, rotating like that. It's not like that. According to quantum mechanics, it's neither. It's a superposition of both. And when you measure it, you will get randomly either one or the other, with a probability of 50% and 50%. That actually is one of the postulates in quantum mechanics. It's the so-called Born probability rule, one of the postulates in quantum mechanics. And so the act of measurement with a microscopic instrument, when you measure the spin and you get spin up, that's fundamentally unpredictable, because it wasn't up, it wasn't down before you measured it. It was in a quantum superposition, which means even if we had absolute, complete information about the state of this room before we perform the measurement, and the room is isolated, nothing enters, nothing leaves, we have information about everything, every single atom, every single molecule, everything about this room, and we have infinite computational power. And we know all the laws of physics. We know everything about physics. Even in that case, we would be unable to predict whether this experiment is going to find a spin up or a spin down. It's fundamentally unpredictable. It's random, whether it's one or the other. Which means that even at the macroscopic level, because our instrument is macroscopic, the instrument will say up or down. That macroscopic instrument, the state after the measurement, is unpredictable. So there is no deterministic sequence of events at the macroscopic level that will allow you to say whether this macroscopic instrument will say up or will say down. So you see, this is happening at the macroscopic level when you put it in interaction with a microscopic one, that elementary particle. And so, in that way, even the macroscopic world, somehow it gets, how can I say it, contaminated by the randomness, by that chance behavior of the quantum world.
Yeah.
Which, to me, and I think this is one of the, it would be one of the important lessons from the whole thing. It would mean that the future is not predetermined. So what's going to happen an hour from now is not rigidly predetermined. It's not like some people say, what's going to happen will happen. We may not know what's going to happen, but it will happen. According to quantum mechanics, and my understanding of it, and a large fraction of physicists, that's not it. Okay, the future is open. There are different possibilities. It's not fixed, it's not predetermined. Quantum mechanics is not deterministic. And so, another way of saying it is that the future doesn't exist.
So even macroscopic level. So do you think that in somewhat, or in some sense, similar to double slit, experiment? So
The two-slit?
Two-slit, double slit.
Right, yeah, there is connection between the two, because in the two-slit, when the particle is coming toward the screen with two slits, because you have two slits, it goes into a superposition. And so if you say which slit it went through, you cannot say. In a way, it's like it went through both. That's analogous, that's similar to saying that the particle was in the two spin states, either spin up, spin down. It was in a superposition of both. If you say, but is it one or the other? You cannot say unless you measure it. Before you measure it, it's not in one or the other, it's a superposition. The same with the particle going through two slits. You cannot say it actually went through this one or that one. In some sense, it went through both. And it doesn't mean that the particle splits in two. And you have now two particles going through, it's not like that either. And if you put a tiny detector at one of the slits, and even if the detector doesn't detect anything, well, if it doesn't detect anything where the particle is about to cross, it means it went through the other one, which changes completely the behavior of the experiment. Now you can say, oh, because I did not detect anything here, it means it went through the other one. Now it's no longer in a superposition. That breaks the superposition. That's the terminology in quantum mechanics, as you know, is the collapse of the state. You are collapsing the state. Even if you didn't find the particle going through this slit, you are collapsing the state. It's no longer in a superposition, and that changes things. And that happens every time that you perform an observation, a measurement. You collapse a state, and that is what introduces this chance behavior, this randomness, which again happens at the microscopic level, and the question is why? And nobody has a good explanation of that. I mean, nobody knows whether collapse is real or not. Now, if there is no collapse, if collapse is not real at all, and you eliminate that postulate from the foundations of quantum mechanics, from the set of postulates, then you have a theory which looks exactly like quantum mechanics but without the collapse, and a theory that implies that all possibilities become actual. Anything that can happen actually happens, which essentially means that the universe is constantly branching out into multiple copies of itself. And that's the so-called many worlds interpretation of quantum mechanics, that, which would imply that instead of just one universe, we have a multiplicity of parallel realities. So in other words, there is you and me here talking. There is another version of you and me talking in a parallel reality in which things are almost exactly the same except for minor details, like maybe this is in a slightly different location,
Mm.
things like that. So there's virtually an infinite number of parallel realities, and from that point of view, if there is no collapse in quantum mechanics. So, so you see, the reason this actually fascinates me so much is because it has some very deep philosophical consequences, not just for physics experiments, our understanding of physics, but also deep philosophical consequences. For example, if there is a fundamental randomness and the future doesn't exist, maybe even the next microsecond doesn't exist, it's not determined. It is when it is. When it happens, now it's real, but not before. And it has consequences to the way you look at your own life, even from a more philosophical point of view. If you think that your future is predetermined, it's like you are rigidly predetermined, then you have no free will. Everything that happens like we are robots, like rigidly bound to obey the laws of physics, and there's nothing we can do about it. I am going to die this many years in the future in some particular way, maybe in an accident, and there's nothing I can do about it. From that point of view, that rigidly deterministic point of view, I don't believe that's the case. I don't think, because of quantum mechanics, I think that's not the right way of looking at physics. And which also to me is more interesting, because it means if the future is open, I do have some sort of free will. I can make actual free choices. That's an entirely different problem, of course, the problem of free will.
Yeah.
I don't want to go into that one because it's a difficult problem in philosophy. But the foundations of quantum mechanics have relevance to all those areas, even of philosophy. And that actually is one of the things that fascinates me.
So at least quantum mechanics give us hope. So we can change, we can, we can manipulate, we are not...
To some extent, we
Yeah.
are not entirely rigid
Robot.
automatons. Yes,
Okay.
robots, yeah.
Good, good. Well, now let us go forward and ask, what is like, the next, you think, next main problem? Now we mentioned that, gravitational quantum mechanics, and this is the randomness, and what else?
Well, again, let's talk about another problem. Let's not really put it in order, because other people would disagree
Yeah.
with which is more important, which is second, which is third. But
At least
another
in
one
your-
that
in
to
your
me
view.
I think is important. Well, certainly I mentioned before supersymmetry. I myself was actually convinced supersymmetry would be found at the Large Hadron Collider. I remember telling my students years ago, you can take my word for it. I mean, when they start operation at the Large Hadron Collider, they are going to find supersymmetry. I was wrong. I was completely wrong. And they did find the Higgs boson, which was a very, very important discovery.
Yeah.
But supersymmetry would be much more important than the Higgs boson. The Higgs boson was expected to be there, since 1967. It was the last ingredient of the standard model of particle physics. But it wasn't revolutionary because it was expected. In fact, some physicists were hoping that they would not find the Higgs boson because that would have meant, the new physics needs to be explored. But they did find the Higgs boson, but they did not find supersymmetry.
Mm.
So that's a big puzzle. What's going on? Why? And what to do about it?
Higgs boson is it's critical ingredient of quantum or particle physics. So.
Oh yeah, it's absolutely central to the standard model of particle physics.
Mm-hmm.
Yeah. So it was a very important discovery. But again, by discovering the Higgs boson, and of course the Nobel Prize was given to those who originally had proposed the Higgs, the so-called Higgs mechanism in particle physics. Higgs himself, although it was 3 groups, 60 people in total. Some of them already passed away. It was important, but again, it wasn't revolutionary because it didn't really teach us a lot more about physics. We already knew since the 1960s the physics of the Higgs mechanism and everything, and so It was just a confirmation that we were on the right track regarding that. Discovering supersymmetry would open entirely new vistas. I mean, it would explain lots of stuff that so far is unexplained. There are some important problems in particle field, like for example, the hierarchy problem, the so-called hierarchy problem. Another problem, it may actually explain dark matter, because if supersymmetry is right, then there should be more particles that we have discovered in nature. For every elementary particle, there should be a so-called super partner, supersymmetric partner, which differs in spin by 1/2. For example, for the photon, which has a spin 1, there should be, if supersymmetry is right, there should be a supersymmetric partner which is known as a photino with spin 1/2. And that, for example, that particle would be an ideal candidate, it is an ideal candidate for dark matter. So if supersymmetry is right, maybe photinos do exist, and that probably would explain what dark matter is, if they were produced in large quantities during the Big Bang. On the other hand, if supersymmetry is not right, then most likely photinos don't exist, or any other supersymmetric particles that could explain dark matter. So supersymmetry is still a deep, brilliant idea that has been explored extensively over decades, but the fact that no indications at the Large Hadron Collider happened, that's a big puzzle. To me, it's an important problem. Whether or not that's the third most important one, that's not necessarily the case, but it's a really important one.
But do you think that the only way to prove the supersymmetric is like through the Large Hadron Collider, or this is the only possible now?
Well, right now it's the only feasible one, yeah. But that doesn't mean it's the only way. I mean, it's conceivable, although very unlikely, that they could find evidence in cosmic rays, for example. They are extremely energetic, but we need more than just energy. You need the density, the energy density, to be high enough to see enough number of events per unit time. And so, but who knows? Maybe at extremely high energy cosmic rays, supersymmetric particles are produced, and maybe one of these days they will find evidence. Again, it's very unlikely, but that is not the only way with the Large Hadron Collider. The thing is that the Large Hadron Collider already had the energy expected based on different ways of implementing supersymmetry in particle physics. They were expecting that evidence would be found at these energies. It may be that you need to go to even higher energies, but that already eliminates all the simpler versions of the simpler implementations of supersymmetry. So it makes it less likely to be true if you start pushing to higher and higher and higher energies.
Yeah.
But it may still be the case.
Well, do you think that supersymmetry has something to do with what's called, matter and antimatter, balance in the beginning of universe?
Right. Yeah. That's a good question. That's a good point.
Yeah.
I said before, many supersymmetry could answer many of the other unanswered questions, like the hierarchy problem, maybe dark matter, etc. That's another one, actually. The fact that there is an imbalance between matter and antimatter, that's another fundamental problem in physics, really. Whether you put a number 4 or 5, but it's another important one. Why is so much matter and so little, almost no, antimatter in the universe? How that happened is a mystery. And the way we understand it, which is a partial understanding, is based on ideas that Andrei Sakharov, a Russian physicist, proposed in the 1960s, which has to do with CP violation, or time reversal violation of the laws of physics, plus another two ingredients. One is C violation, charge conjugation violation, and also baryon number violation, and also processes far from thermodynamic equilibrium. Well, the key one there is time reversal, or CP violation. It does happen in the standard model of particle physics, but it's not strong enough to explain this imbalance between matter and antimatter. in the universe? Well, supersymmetric theories, if you incorporate supersymmetry into particle physics, then you will have other sources of CP violation and time reversal violation, much stronger than the ones in the standard model. That could explain if some supersymmetric particles were involved in processes in the early universe, that could explain that stronger CP violation that would give rise to this imbalance between matter and antimatter. So that would be another important problem solved if supersymmetry is correct, but doesn't seem to be. So,
well, let us, at least choose one, because now we mentioned 4. I mean, can we like?
Well, I can mention one more actually.
Yes,
that probably I should have mentioned slightly before.
Yeah.
And some people would put it probably at the top, maybe number 1 or 2, close to the top. The issue of black holes and quantum mechanics.
Mm-hmm.
The fact that if event horizons actually exist, which, I mean, for an ideal black hole, when we understand black holes, they always have an event horizon. It's kind of like a one-way boundary. You can enter, but you cannot leave. If those one-way boundaries, these event horizons, actually exist, then it was discovered by Hawking, Stephen Hawking in the 1970s. Then there is a problem with quantum mechanics. That seems to clash with quantum mechanics. It's inconsistent with quantum mechanics. Specifically, with one feature of quantum mechanics, which is called unitarity, the unitary evolution, the Schrödinger equation, basically. So it's inconsistent with the Schrödinger equation. This has come to be known as the information loss paradox. And to this day, and that's been a long time, since the 1970s, it hasn't been fully resolved. It's a fundamental question that nobody has been able to answer in a way that it satisfies everyone. Hawking initially thought that maybe this means quantum mechanics is wrong and needs to be modified. Other people, Leonard Susskind and others famously were in disagreement with Hawking. They thought, well, most likely quantum mechanics is right, and if anything needs modification, probably general relativity needs to be modified, and not quantum mechanics. They felt more confident in quantum mechanics than in general relativity. We still don't know what's going on. And in fact, that paradox, that problem has morphed, has changed into something even worse. Not many years ago, another paradox is called the firewall paradox was proposed that essentially says that if you are freely falling into a black hole, instead of going through the event horizon and entering the black hole, you will be destroyed by a flash of radiation right before you hit the event horizon. Maybe event horizons don't exist. You just have this firewall, this region where there's a tremendous amount of energy, like a flash of energy that would incinerate you and destroy you. That violates...
This energy are like Hawking radiation?
It would be kind of like that. I mean, it would be a very intense radiation, yeah. But the problem is, it violates general relativity. The principle of equivalence tells you that if you are freely falling, you would feel like you are in an inertial frame. There should be nothing special about crossing the event horizon. You shouldn't feel anything. The fact that you encounter this flash of radiation is inconsistent with the principle of equivalence. But it is a consequence of assuming the basic things we assume about the validity of quantum mechanics and other things. So that is another big problem right now. How to explain that? Perhaps many of those problems will go away if we say that event horizons don't exist, period. Hawking himself, actually, in 2005, I believe, did propose that. He said, well, maybe event horizons don't exist. Why? Maybe because of quantum mechanics. Maybe because of quantum mechanics itself, event horizons never actually fully form, really. In which case, we solve the information loss paradox, and presumably we could solve also the firewall paradox. So these are really important things, and it actually, it probably points the way toward a quantum theory of gravity. Maybe if we have a quantum theory of gravity, we will be able to answer those questions and solve the information loss paradox or the firewall paradox. That's also the hope for a quantum theory of gravity, to allow us to resolve those problems. Connected with these problems, connected with the idea, with these paradoxes and quantum gravity, there's the issue of what many think should be a fundamental new principle of physics, the holographic principle. They have tried to use it to explain away the information loss paradox and other things. And eventually, in the 90s, it was found that it was proposed, this conjecture, the so-called ADS-CFT, anti-de Sitter space conformal field theory conjecture. It's basically an equivalence between the physics in a region of space-time and the physics on the boundary. That's the holographic principle. It was a specific implementation in the context of string theory. And it has become, since the 90s, it has become, the paper was written by Juan Mandacena, has become the most cited paper in the history of particle physics and quantum field theory. It's amazing that in 20 years or so, it has become the #1 paper in terms of citations in theoretical physics, essentially. It's an indication that physicists, theoretical physicists, think that this is really, really important, and it would probably help us answer some of these fundamental questions, and maybe it is already pointing the way to a quantum theory of gravity. There's a lot of work in that area now. I mean, working on trying to explain gravity in this four-dimensional space-time, say, by analyzing quantum fields on the boundary of space-time, on the boundary of this region. So instead of using string theory or trying to do a quantum theory of gravity here, they are working with quantum field theories, specifically conformal field theories on the boundary, which are not gravity theories, to explain gravity and the physics of space-time. Maybe even they are actually trying to derive Einstein field equations with that approach. Which is very exciting. I mean, it's a very, but still, there's a lot of work to be done. I mean, this is only in the beginning stages. It's not that they have actually found the answer to any of these questions yet. So,
just last question, since we mentioned the black hole again, what do you think is the singularity of black hole? We know that there's the event horizon, and still it is controversial, as you say now. But what about the singularity itself? If we get to the center of the black hole, if we imagine, or if we can
the singularity, according to the equations of general relativity, when you look at the solutions, for example, in the case of a Schwarzschild black hole, the singularity is a region where space-time has infinite curvature. And so the gravitational, the tidal forces are infinite, and essentially it's a point where all so-called space-time geodesics end. It's like the end of this geodesic, so it's like the end of time at that point. It essentially doesn't make sense. It's an indication that the theory is making a prediction that is probably not right. So for a long time, outside the context of quantum mechanics, I mean, people proved theorems, Hawking and Penrose and others proved some really important theories about the necessity of singularities as consequence of the field equations of general relativity. So from that point of view, classical general relativity, singularities had to be there. They had to exist, they had to develop in space-times, in realistic space-times. The problem is that the singularities indicate that over there, general relativity breaks down. General relativity at a singularity breaks down. It's like, it's a prediction from the theory that means that the theory doesn't work there. because space-time curvature becomes infinite. So there has always been suspicion whether those singularities are real, they would actually develop or not, and how. Still in the concept of classical general relativity, the question was, is it possible to have singularities in space-time floating there by themselves? And the general feeling was that no, probably that's not the case. And they couldn't find solutions on Eisenfield equations with so-called naked singularities. And so they conjecture, well, maybe they're always covered by an event horizon.
Censorship, you know, conjecture. It's called censorship.
Yes, exactly. Roger Penrose proposed that cosmic censorship conjecture. Yeah. Like there are no naked singularities, so they're always covered by an event horizon. So because event horizons don't let anything escape. The problem with this is that quantum mechanics, mechanics apparently actually allows things to escape. One way of looking at it is that stuff is actually tunneling through the event horizon out. Another way of looking at it is that pairs of particle-antiparticles are produced outside the event horizon. One of the particles goes inside, the other escapes to infinity. The one that goes inside carries negative energy, and so the mass of the black hole decreases slightly every time a particle is emitted. That's Hawking radiation. But again, that's a quantum mechanical process, which violates some of the assumptions in classical general relativity. Some of the so-called energy conditions, like the null energy condition and other positive energy conditions in general relativity. Actually, all the energy conditions, like the weak energy condition, the strong energy condition, they're all violated by quantum mechanics. Most likely, quantum mechanics would also prevent the formation of singularities. Maybe at the microscopic level, when a singularity is trying to form, quantum mechanics would not allow it to form. Maybe at that scale, maybe at the Planck scale, because perhaps space-time is no longer space-time, it's not described by general relativity, all those singularity theorems would not apply. They are no longer valid because they are actually proven in the context of general relativity. But if general relativity doesn't apply at this scale, because space-time is no longer a smooth manifold, differentiable manifold, it's something else, then there would be no singularities. But again, that would be most likely a consequence of quantum mechanics. Maybe there are regions of extreme space-time curvature, but not true singularities, not infinite space-time curvature.
Nice. Well, let us now just list or wrap up and summarize what we just mentioned. I think we list the main unsolved problem, like from theory of gravitational quantum gravity. Then we mentioned, I think,
all the foundations of quantum mechanics.
Yes, foundation and randomness, and also we mentioned the supersymmetry, and we mentioned.
Well, we mentioned this one, the information loss paradox, so the firewall paradox, and the holographic principle.
Right.
But it's connected also to quantum gravity, etc.
Yes,
and quantum mechanics.
Yeah. So you think that almost the central unsolved problem is the quantum gravity?
Somehow, quantum mechanics is central to any of these fundamental problems. Quantum mechanics is there. And certainly understanding how to combine quantum mechanics and the physics, a fundamental physics of space and time, which would be a quantum theory of gravity, is really, really basic. There are lots of other open problems in basic physics, the cosmological constant problem, etc. But of course, we could spend 5 more hours talking about.
But do you think those are not related to quantum?
Some of them maybe. Some of them maybe.
Yeah.
And in fact, I suspect that solving one of these fundamental problems may actually automatically solve.
Right.
Or partly, or in part, solve many of the other ones. We don't know, but it's possible. Yeah.
Okay, Rafael, what is your final word, especially for Arab audiences?
Arab audiences. Well, I've always been actually fascinated and grateful even by all the science that was developed in the Middle Ages by the Arab world, medicine and astronomy, mathematics. While the rest of the world was actually really in the Middle Ages, in the Dark Ages, intellectually. The Arab world was flourishing. Intellectually, it was really important in the history of science. And so we all have an important debt to the Arab world. And so I'm happy to, with this short interview, give something back.
Good. Well, at the end, I would like to appreciate, to thank Dr. Rafael for his time.